At the first video of this chapter, I had mentioned that we're going to talk about ionic and covalent compounds. We're going to compare them. And then at the second half of the chapter, we would just focus on covalent compounds. So this is the point where we're just going to branch away. We're going to only focus on covalent compounds from here on out. And in chapter 7, we will come back and learn about ionic compounds more specifically again. So the first thing you need to do for this in naming is you should know that covalent compounds tend to form between a nonmetal and a nonmetal. That's because the nonmetals are in the upper right of the periodic table, which means they're all very electronegative. That means that anytime two nonmetals bond, the difference in electronegativity is usually going to be pretty small. And because they both really want electrons quite desperately, because they're all highly electronegative, they tend to share because neither one is able to steal and get the upper hand enough to steal, so they end up sharing. So that's why covalent compounds are nonmetal. Now you have two elements that make these up. Binary means two, so we're only going to be talking about covalent compounds with two elements. Now the first element that you write is usually the electronegative. So if you're wondering what order you put the elements in when you write them and name them, you usually put them from less electronegative to more electronegative as the second element. And then for the first element, you only include a prefix if there is more than one of them. However, for the second element, it always gets a prefix. So for the first element, if there's only one of them, you do not include a prefix. The second one, doesn't matter, always gets a prefix. And we will talk about the prefixes in a minute. For now, just write down that rule and just kind of keep it in the back of your mind because we'll use it in a second. Now for the second element, you also have to add an IDE ending to that element. And I'll show you examples on not this slide, but the next one. For this slide, I have your yellow sheet here. Take a look at it. You'll see over on the left side, you have a list of all the prefixes. Now, you do not need to memorize these because you get to use your yellow sheet on every test. So make sure that you remember where this is at and that you have access to it. So you got mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca as your prefixes for the first 10 numbers. Now on the back page, if you flip your paper over, you have all the IDE endings over here. Well, actually I should say all of them, but most of them. So what we mean by IDE ending is if oxygen is your second element, you would label it as oxide. Nitrogen becomes nitride, phosphorus, phosphide. So always remember that this is there because I have students on a test that will ask me, how do you change phosphorus to an IDE ending? They can't remember if it's like phosphoride or what it is. And I always tell them, you don't need to memorize this. Check your yellow sheet. So remember that it's there. There are 4 elements though: iodine, fluorine, chlorine, where is it? There we go, and bromine. These are your halogens. I don't have these listed over here. There is a rule to coming up with IDE endings for these though. Notice how they're all INE: bromine, chlorine, fluorine, iodine. To change these to an IDE ending, you just swap that N for a D. So iodine would become iodide. That N becomes a D. Chlorine would be chloride, fluoride, and bromide. So make sure you know that rule. So here's some examples. The first one, we got 2 elements. In the rule, remember when I said make sure you put the less electronegative first and the second, or the more electronegative second? Whenever I give you examples like this, I already have them ordered correctly. You just have to name them in the order that they already are. And same thing goes for the reverse. So you don't actually have to really worry about that rule. So for the first one, N comes first, so I'm going to name it first. It is nitrogen. And then oxygen becomes oxide. Now the rule for the first element is it only gets a prefix if there's more than one. and there's only one because there's no number there. So no prefix goes right there. The oxygen has two of them, so I have to put dioxide. So this one would be called nitrogen dioxide. For the second one, you probably recognize this right away as water, and you're absolutely correct. And that's how every chemist ever calls this compound. But there is the official name. If we write it out, the official, it's IUPAC. I forget what that stands for, International Union of Applied Chemistry or something like that. There's a whole council of people that come up with the rules of how to name these compounds. So we got hydrogen and oxygen. Oxygen turns into oxide. Anyway, so we're coming up with that official, following the rule book name. But again, no one actually follows that rule for water. They just call it water. It's so common that it has its own special rule name that breaks the rules. Okay, so the first element only gets a prefix if there's more than one, and there is. So I go di. Now the second element always gets a prefix even though there is only one. And then mono is my prefix, but what I do for that is I just go MON, it's monoxide. So anytime you have OO like this, you drop one of the O's. Same thing if you end up with AO, you usually drop the A. So if we did tetraoxide, let's say there are 4 oxygens, it would just end up being tetroxide without the A in there. So we drop double vowels. So this one is dihydrogen monoxide. That's the official name for hydrogen, but everyone actually just calls it water. Oops, okay. Now we're going to do the reverse. We're going to go from the name to the formula. So carbon is C. There's no prefix, so there's only one. Oxygen has di in front of it, so that means there's 2. So it's CO2. And no one ever actually puts a 1 in there. Even though there's only one carbon, you never put a 1 in. So carbon, one of them, dioxide, 2 oxygens. Now the next one, notice this one's pentoxide, but it should be penta, or the prefix is penta, but they drop the A because it's pentoxide. So let's go over nitrogen is N, oxide is oxygen, tri is 3, and penta stands for 5. So 3 nitrogens, 5 oxygens. So that wraps up naming and writing formulas, but there are some notes on covalent compounds. Remember, we call a covalent compound a molecule. So going back to this example, we have a CO2, we call this a molecule of CO2 or a molecule of trinitrogen pentoxide. Now a molecule is the smallest unit of matter which can exist by itself and retain all the properties of that substance. So it's for covalent compounds and is the smallest form of a compound. Do you remember how I gave you the whole example how an atom is the smallest unit of an element? Well, this is pretty much the exact same thing. A molecule is the smallest unit of a compound that can exist. So if you had one molecule of H2O, that's the smallest piece of water I could physically have. If I were to break this up anymore, it's no longer water. Now, write this down. There are diatomic atoms. Just write that down. It's not really important right now. But notice that they're not always in the lowest ratio. When you deal with ionic compounds, you always write them in the lowest ratio. But for covalent compounds, you can have C2H6. Notice this is not the lowest ratio. If you had an ionic compound on the other hand, like Na5Cl5, you'd never actually write it like that. You would reduce it down to NaCl. Or Ca2Cl4, you would always write it as CaCl2. Ionic compounds you always reduce to their lowest ratio, but covalent compounds you don't, because you want to, if you remember, covalent molecules are their own little thing, and I need to say how many carbons and how many hydrogens are in that thing. Whereas NaCl is a crystal structure, And if I say there's a 5-to-5 ratio of them, well, I might as well say there's just a 1-to-1 ratio of each atom in that crystal. Or in this case, there's a 2-to-1 ratio or 1-to-2 ratio. I would never say there's a 2-to-4. So that's why we always use simplest ratios for ionic, but not necessarily for covalent. Okay, so the diatomic atoms. Now we're going to talk about these. They are molecules containing 2 of the same atom. Here are the examples, and you don't need to memorize these because they are on your yellow sheet right below your IDE endings. So these elements, so like oxygen, it never exists just as a single O in nature. If you find pure oxygen, the oxygen we breathe is actually O2. Same thing, the nitrogen that's in the atmosphere is N2. This is the elemental form of these elements. They come attached to themselves. And it's super important to remember them. Some other examples, P4 and S8. Those are the elemental versions of phosphorus and sulfur. You need to know them for the test, but you don't really need to know them because you have them on the yellow sheet. You just need to know that they're there, and you need to remember to use them when appropriate. And they are all considered elements. So we consider all these elements. Now, you might be like, well, this technically it is a molecule because it is 2 atoms bonded together, but because it's the same atom, we still call it the elemental version of oxygen. And this is important because when chemists were first trying to figure out like the ratios of like masses of atoms, they would react them and figure out what's the ratio of mass of this to this. And the masses on the periodic table were relative masses, and they were usually compared to hydrogen, but no one knew that hydrogen was actually H2, so all the ratios were off by a little bit. So it was really important that they figure out, oh wait, hydrogen and oxygen are actually diatomic, and then that allowed them to figure out the ratios of these reactions a lot better because they weren't accounting for the fact that there were 2's here. They thought it was H plus O goes to H2O. So that solved a lot of problems figuring out these diatomic atoms. Okay, the molecular formula shows the type and number of atoms combined in a single molecule. So nothing new there, right? We already talked about that. If you have H2O, this is the molecular formula. It tells you which atoms and how many of each are there. 2 hydrogens, 1 oxygen. Not necessarily the lowest or simplest ratio. And oxidation numbers do not work all the time. That doesn't mean anything to you yet. We'll talk about oxidation numbers at the start of chapter 7. But the oxidation numbers help us try to figure out in what ratio things bond. It doesn't always work for covalent, but it does always work for ionic compounds. So examples of molecular formulas. Sulfuric acid is H2SO4. That would be an example of a ternary compound. We've only talked about binary that have 2 elements, H and O. This has H, S, and O. And then ethane here, I use that as an example. Notice that is not in the simplest ratio. So that's what you need to know. Make sure you remember how to write out covalent names and write out covalent formulas. And then just make sure you know what a molecule is and molecular formulas.